Okay, guys, this is Bitcoin, a peer-to-peer electronic cash system. Uh, this is also the title of the white paper written by by someone that we don't know who it is actually, which presented himself as Satoshi Nakamoto, that first described the system. The current Bitcoin protocol has evolved and has some features that Satoshi did not envision, but I will try to stay pretty much with the white paper structure, and maybe we can discuss in later sessions upgrades that happened to the protocol. Okay, and this is also based uh, on the fact that Bitcoin is an open protocol, so anyone can implement their own software and connect to the network. But in practice, around 99 or 98% of the whole network today runs one reference implementation that's called Bitcoin Core. So what I will say here is how things are implemented in Bitcoin Core, but there may be some other implementations out there, right? And I usually leave this slide to the end, but since this can become a controversial topic of discussion in the Discord channel, I would like to begin with some credentials, not to say that I know everything, right? But my name is Edu Medeiros. You all know that I'm a professor at the Electrical Engineering Department at the University of Brasilia. I study Bitcoin as a monetary phenomenon since around 2012, 2013, but I recently started digging into the nitty-gritty aspects of the Bitcoin protocol. And you'll also have my contacts here. Feel free to reach me out and say that I'm wrong or say that I'm a genius. I don't know. It's up to you. And everything that will show you is based on three main sources of information. The first one is the white paper itself, which was published in October 2008 by this entity that we know by the name of Satoshi Nakamoto. It's freely available on the internet. Just Google it for Bitcoin white paper and you'll find it. And it's an easy read. It's an easy thing to read. Uh, the other source is a book called Mastering Bitcoin by Andreas Antonopoulos and David Harding. Andreas is considered one of the best teachers, quote unquote, on this Bitcoin space. So this is actually a very instructive book. And of course, I am using the source code of Bitcoin Core itself. This is the reference implementation, and everything is open source on GitHub, so you can go there and clone the repo and read everything. You don't have to trust me, so just get the sources and learn by yourself. And what I'll try to do here is give a bird's eye view on the protocol to speed the learning curve of beginners. And I consider myself a beginner still, so I'm trying to learn also by explaining things for other people. And the first message I want to 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 state here, and maybe this is the main message I want to say to anyone interested in this whole thing, is that Bitcoin is actually a digital messaging protocol. It's nothing more than a computer protocol for exchanging message between people. It's not much different from, for example, WhatsApp or Telegram or whatever. Or even it's not much different from, at least from this perspective, it's not very much different from the messaging systems that are used today for banking stuff, for banking business, just like credit card things and home banking. It's not that different, at least from this perspective here. But you will see there are some fundamental differences because the problem Bitcoin is trying to solve is fundamentally different from other messaging protocols, right? Uh, I also usually don't include an agenda slide, but this is pretty much what I want to talk about. Everyone likes to say blockchain is the important thing. I don't believe so. Uh, so I will try to keep this agenda, but since this is a work in progress, I may decide to add some things in between, and I will use this agenda here to locate ourselves between different sessions. So let's start by with the problem Bitcoin proposes to solve, which is to create an economy based on digital transactions. Or this is something that already happens. This is I will try to say what happened and how did we abstracted money and give some context about the Bitcoin problem. So let's start with an economy that's in which transactions are mediated by physical money. So think like silver or gold or shells or salt or whatever good or whatever commodity you might think was used as money in the past. So there is every transaction is a two-party thing. So you give here Alice gives Bob some kind of money, let's say silver, for instance, and Bob gives some food for Alice in return. So this is the whole transaction. And it's easy to see that Alice can't spend this physical coin in more than one transaction. This is the first problem that arises when we are talking about digital things, because things are too easy to copy. In the physical world, things are not that easy to copy. For example, it's very hard to make gold. People are trying to do this, try to do this for a lot of time. Think alchemy and all this, that stuff, right? And uh, it's not that easy, but it's feasible to Bob to check if the money or the commodity LC is offering. He can check this is not a counterfeit. So it's not that easy to check that gold is gold. It's not that easy to check that silver is silver indeed, but it's feasible and people actually do it. Uh, but we have this is kind of inconvenient, right? Because carrying gold around or silver around it is not the best thing, and you can of course understand this is dangerous. It's not only inconvenient because it's you are carrying something that is highly valued in the market. So what people start to do, they they go into something that I will call a bank, and I will use this bank for whatever intermediary is acting on behalf of money here. So Alice goes into this institution, deposits the physical money, and gets uh, some certificate back. It's like paper, and actually this is a picture of a certificate that the United States Treasury emitted in 1899. This was before the central banks even existed in the US. And it's quite interesting to see it in more detail because it reads this it reads here in the top of the bill. This certifies that there has been deposited in the Treasury of the United States of America $1 silver, and a dollar is a standard amount of mass, if you will. Also here it's saying this is payable to the bearer on demand. So anyone can take this bill and go back into the bank and redeem some amount of silver, which is equivalent to $1. So this was the definition of $1 in the past. And also in the back of the bill, you can read this certificate is receivable for customs, taxes, and all public dues, and when so received, may be reissued. So there are two important things here that are written here. First is the government itself recognizes this as a valid thing to pay taxes, which is the most important thing for government. And also, there is also a subtle thing here, which is this can only be reissued, this bill, when it is redeemed, when it goes back into the treasury. So it cannot print this bills at will. It will have to print this only when someone presents some silver, and this is to certify that there is some silver in the vault, right? All right. Now, Alice, with the possession of this bill, can use this certificate just like money, and do the transaction with Bob, and later Bob can go into the bank and reclaim the physical silver, thus completing the transaction. But there is also an interesting thing that people started doing. uh, Bob doesn't need to go into the bank to redeem silver. He can use to buy, I don't know, educational services, and the teacher can use this silver certificate to go into a rock concert, I don't know, and get music back. And the musician can go into a cook and buy some food, and the cook can use this for other stuff, and no one needs to actually redeem the silver back. And you see, when we are doing this, when the economy starts doing this, when people start doing this, we actually abstracted money, because there is let's put this way, quote unquote, real money that's on the bank, which are the silver coins, or the silver bars, or gold, or whatever. And there is those tokens that are the paper certificates that there are some money, some real money on the bank. But nobody ever goes into the bank and redeems the real money, right? And people started doing this, and people did this for like centuries, never going, or more or less never going back into the bank. This is why in the 20th century, when governments decided that there will be no more redeemable certificates for nothing, they will become just paper bills that are not redeemable for any goods in the banks. People did not even notice that this happened. Just things just kept going, and it's like they are today. But still, paper is not, it's not the most convenient thing in the world, because we can still lose the bills, and be and in consequence lose our capacity to transact with other people, right? So more recently in history, we started doing something a little bit different, which is way more convenient, actually. We went into this bank, deposit some, we go to the bank, we deposit some funds. It doesn't matter here if it's just paper or if it's gold or whatever, but you go there and you deposit some funds, and the bank issues a electronic card for you. And this is a very strange thing, because now what we do when we want to transact is we send a message to the bank, a digital message. It's like a note or check, then we sign. Here we use this card to create a digital signature, and we send this to the bank, and the bank sends another message to Bob saying, "Oh, I see that Alice is transferring some funds for you, and I will guarantee that you are okay and you are going to receive your funds." And in receiving this message, Bob can just complete his non-monetary part of the transaction. So in this scenario, we abstracted money a little bit more. I would say a step more, because we are not even dealing with physical things anymore. we we still can go into an ATM or in the bank itself and redeem some paper bills. But actually, the most part of the economy in the developed countries and in Brazil as well are functioning based on messages that are just digital messages being issued, being transmitted between people and the bank and between the banks, right? And those messages are very standardized, actually. There are two important standards, uh, which are the ISO 8583, which defines bit by bit what flags and what the bits mean into the credit card messages and banking messages. And there is also also another standard called EMV standard, which stands for Europay, Mastercard, and Visa, which was a consortium one of companies that developed the first credit card standards. And it's also a communication protocol. They say, okay, this bit will mean this, another bit will mean this other flag, and stuff like this. It's very low level thing. For us computers. And I'm not here to say banks are useless or that banks are evil or whatever. On the contrary, banks have a lot of important functions for the economy, not only for these peer-to-peer transactions or serving as intermediary of transactions. They have to at least keep the user's balance. So it's up to the banks to say how much money everyone has in the system, and the bank is responsible for clearing transactions. And this is a technical term, which means simplifying a little bit, but it means to check the availability of funds when I want to spend to pay, let's say, Lemos 10 reais or $1, the bank has to check if I have the funds, the enough funds to make this transaction. And also, it is the bank responsibility to timely transfer those funds, right? So if I'm transferring funds from my account to Lemos account, for example here, and we both have accounts in the same bank, it's just writing something on a database. It's like instantaneous. But maybe I have an account in one bank and Lemos has an account in another bank. So those banks have to communicate, and they have to exchange some messages to say, oh, someone here is trying to pay someone there, and they have the funds, and they have to synchronize all those things. This is also clearing, the part of the clearing of the transactions. And actually, this takes a few days to happen. It looks like it's instantaneous for us, but it actually takes a few days. And for credit cards, it's even worse because the credit card company can take up to 60 days, like 2 months, to actually clear transactions. So this is a very long process. Uh, uh, in practice, this everything here works quite well. We all use banks and other third parties as credit card issuers, as digital payment intermediaries pretty much every day, but the system is not free of problems. And one of the main issues here is that both parties must trust the bank. Uh, Alice, on her side, must trust the bank will not refuse her transactions. And on the other side, Bob must also trust the bank will not issue bills with no collateral. So Bob has to trust that the bank is not, I would say, print new money just to fake a transaction or whatever. And of course, there are a lot of controls on this thing, as you can imagine. But uh, shit happens, as we can say. I consider myself a faithful citizen here in my country, and I have had legitimate funds blocked, and I have had legitimate transactions refused by banks before without doing anything wrong, at least not formally wrong. So shit can happen. Error can happen. Errors can happen. Bugs in computer systems can happen. Government corruption or authoritarianism can happen, and the bankers themselves corruption might happen. So a lot of things might happen, and in this whole setup here, the bank is a single point of failure. So uh, this is big shit because banks are serving as intermediaries in virtually every single economic transaction in society. So if disruption happens here, we are talking about disrupting money, and everyone uses money, and everything is pretty much based on money, and ever was. So the whole question that Bitcoin is trying to answer is, can we design a digital payment system without a single point of failure? And you see, it's not about banks, it's themselves, right? It's about not having single point of failures. Or can we make digital transactions without the need to rely on a third party? Can we do peer-to-peer digital transactions? This is the question that Bitcoin is proposing to solve. And it's this is actually not a trivial task. Some really smart people tried before to accomplish this and failed miserably. So it's no wonder the current system is based on central authorities and banks. It's not because they are evil and they want to impose some kind of agenda on us. This is a technical requirement, or at least this was a technical requirement until recently, right? So this is the problem Bitcoin is trying to solve. So we go to our next topic here, which I will explain for you what are the Bitcoin transactions. And the Bitcoin transactions are actually there is kind of a consensus on the technical community right now, which is to consider the Bitcoin transactions the most important part of the Bitcoin system as a whole, and not the blockchain itself. Everything, every other piece of the Bitcoin protocol and the Bitcoin system is designed to ensure that transactions can be created, propagated, validated, and added to the global ledger of transactions. And this global ledger is the blockchain. It's just a data structure that will exist to make a record of these transactions. And of course, it's doing a little bit more things, and we are going to talk about the blockchain functions in a later session. So let's go back to what we are trying to do. Instead of sending Alice is sending Bob a a paper bill. What I want to do is to send Bob a digital message, and I want to him, and I want him to receive this message and be able to validate this message and trust that he will have his funds and complete the other non-monetary part of the transaction. So, what the white paper says about this. Uh, I will read the actual quote, so keep with me. We define an electronic coin as a chain of digital signatures. So take note of this word, an electronic coin, because I will use this a lot, and I will explain better what it means to to be a coin here in the system. Each owner transfers the coin to the next by digitally signing two things: a hash of the previous transaction and the public key of the next owner, and and adding this to the end of the coin. A payee, and the payee is someone that's receiving the coin here can verify the signatures to verify the chain of ownership. So let's decompose this. A transaction in the system will be a standard message that will part of a ledger. And a ledger is just a book with a lot of these transactions put together in a specific order. Each transaction has to state a few things. First, it has to say from where money is coming from. So Alice here has to say, I have money that I received from whatever, whoever that I received before. Those will be the information that will be present on the inputs to this transaction. Also, the transaction has to say who's receiving this money, where is this money going to, okay? And those will be recorded on the transaction outputs. So the important thing here to understand is inputs are money or are tokens or coins that someone is trying to spend, and outputs on a transaction are coins that someone is receiving, right? Inputs are coins that someone is trying to spend. Outputs are coins someone or someone else is receiving. Okay, this is the first important concept here. There is this concept of fees. I will leave this for later.
I have a question.
Oh, sure.
Can you send stuff to yourself?
Can I? Oh, yes. And this is an important aspect of the protocol, and you will see why in a few seconds.
Okay.
All right. I will use this specific example so we can see real data taken from the blockchain, from the Bitcoin blockchain that is publicly available. Okay, so suppose Alice received from the Ninja Guy .1 Bitcoin in a previous transaction. So let's suppose she already possesses Bitcoin, this amount of Bitcoin, and it came from this specific transaction here, and she's trying to pay dot 015 Bitcoin to Bob to pay for the carrots, right? This is the scenario we are trying to understand. If we go into the blockchain, and later I can also give you cannot copy a link, maybe, but later I can put in the chat a link to a blockchain explorer that you can actually see those bits here, right? You will find this on page 277.316. This is the block number, which I will consider the page of a ledger. So if we decode this to a more human readable format, we will get this. And the Bitcoin client actually does all this stuff for us. We don't have actually to deal with the byte we don't want, but we can. So this is a data structure that has four fields. It's a record with four fields. First one is a version. It's an integer that defines the semantics for the other fields, and the semantics can be changed on. There is this version field here is used for upgrading the protocol if they want to change semantics of the things. The lock time is um, it's called an absolute time locking thing, and this is information that's used to say things like this transaction will not be valid before January 10, 2015 or 25, for instance. And this locking mechanism is there from the beginning. And actually, this is a very important piece of Bitcoin, the Bitcoin protocol, that allows us to build other other messaging layers over the Bitcoin protocol. So, for example, there is a big hype into this called uh, into this thing called the Lightning Network, which uses Bitcoin transactions, which uses the Bitcoin blockchain, but it exchanges transactions between people without recording everything in the blockchain, and it uses this lock time feature as a security mechanism, so people cannot cheat and people cannot lose funds if they want to use this other network. Next, we have a vector of inputs and we have a vector of outputs, and that's it. So let's look into the inputs and outputs in more detail. So the outputs first, and remember, outputs are coins that someone is receiving. Okay. So each output is just another record which has a value inside. It's this value is pretty much what would be printed in a bill. For example, a $1 bill will have a number one printed there. This is pretty much the same thing. But when I'm constructing the transaction, I can choose whatever value I want to say. So it's more or less like I'm printing a new bill and I can decide what number to write on the bill. Okay. And this is written in units of Satoshi. There is no notion of Bitcoin actually in the source code. You can go into the source code and grab the source code for Bitcoin, and you will only find one or two comments over there. So there is no Bitcoins in the whole system. There is only these units of tokens that you can create, and we call these units Satoshi, right? And the relation that's conventioned is one Bitcoin uh, relates to 100 million Satoshi. So this is why there are eight digits after the digital point here. And there is this other thing here, which is called the script pub key, which is a very interesting part of the system. This is part of a programming language that we will deal in more detail in a few minutes. And this is trying to define who's the owner of this coin that I'm creating with this output. So in this specific transaction, I'm creating two new coins or two bills, one with this specific value here, 1 million, 1.5 million Satoshi. And whoever can solve this cryptographic puzzle defined by this script pub key is the faithful owner of this thing. And why this, you might ask? Why not give someone an ID and say, I'm sending this to the ID, whatever, right? But if we did so, we would require some kind of server or a central database to store this identity, these IDs, and we would need some kind of authentication in the system. But we don't. We want to build a system without central whatever central things are required. So we just make a puzzle, and whoever can solve this puzzle is the owner of this coin of this amount of Bitcoin of this amount of value in the system,
I
and
have
the
a
same
question.
for the other. Sure.
So, is there a particular reason why we need differentiation between Bitcoin and Satoshis? The
No,
only
it
reason I can think of is because one Bitcoin is million Satoshi. Maybe you don't have to deal with floating point bullshit.
everything is in the system is integer numbers, so there are no floating point anywhere.
That's a wise decision.
Of course.
Okay. Okay, so it's just a quirk, I guess.
Yeah, I don't know why people decide this. We probably will never know. We have to ask Satoshi why this he decided for this relationship. So this is it. It's like it is, right? All right. Finally, an input, and remember, an input in a transaction is money someone is trying to spend, in this case, Alice, right? So what is there? We have four things here. The TX ID is the ID of the previous transaction in which the one of the outputs created the coin and which Alice believes she can solve the puzzle that is in that coin. Everyone okay with this? Because I felt confusing.
Okay, so I'm gonna try to repeat.
Okay.
So the TXID is the
Mhm.
ID of the previous transaction in which Alice believes she solved the puzzle.
Exactly. She believes she can solve the puzzle for one of the outputs in this transaction, in this specific transaction, because you saw an example that one transaction can have many outputs,
Yeah, that's
more than
actually a
one.
good question. What is the other output of that?
I don't know. Those are two coins that I'm creating, and they are belonging to two potentially different people.
Yeah, but why would she do that if she's trying to pay Bob?
Yeah, I will defer and answer this in a moment because
Okay.
it's there.
Okay, but Marinho, I think you wanted to say something. Did you get it?
I did, and I know why, because I read a little bit that was in small print in a previous slide.
Mm.
Okay. Okay,
It
so
has to do with transaction fees.
okay.
Yeah, it has to do with transaction fees,
Okay, so
but
the
it
but is everything all right with the TXID? So it's the hash of the previous transaction in which Alice believes she solved the puzzle.
exactly. And the V out is the index which says which output in that transaction she's trying to solve the puzzle. So the TXID with the V out information is something that we will call in the system an unspent transaction output, UTXO. And this is the Bitcoin coin. This is a token of value in the system, right? So going further, the script sig is what Alice believes to be the solution to the puzzle, to the cryptographic puzzle that's in the other transaction, the previous transaction. And the sequence number is something related to time locking as well. The other time lock thing, the one that we saw in the transaction, is a kind of a global thing that refers to the whole transaction. And the sequence here, information here, is referring to only this token here. So we have some more fine granularity in the timing of the things if we want to use this feature, right? So remember this scenario. Alice is trying to pay dot 015 Bitcoin to Bob, and she possesses a token of dot one Bitcoin value. And one important part of the system, and this will answer your question, Amo, is that Alice can own the only thing that Alice can do with a token she controls is to use this as the input of a transaction. So she cannot copy it, she cannot split it, she cannot do anything with this with it. The only thing that this thing can be used to is to be part of one transaction input. And one transaction input that we are seeing here is spending the whole token. It's kind of burning the token because uh, one transaction can only be considered valid if we are trying to spend a token that was not spent before. So if she spends this here and say, but I still have some balance here, some kind of splitting, or if she believes so, and tries to spend the the same token later in a later transaction, that later transaction will be considered invalid in the system. So what she has to do is she has to create another token, a new token, and give it to herself, just like change. Okay. So you can only use tokens once. This is why we had two outputs on that specific transaction. One output is one that she's sending to Bob. It's a new token that she's sending to Bob, and the other one is a new token that she's giving herself.
So every time you have a reminder, you need to send back that to yourself.
Yes,
Okay.
every every time you have change, you have to deal with change yourself.
Okay.
Okay?
So I can't help but notice that that plus that is not the one that we had before.
Yeah.
So that's the fee.
Yes, a transaction will be considered valid if the output sum is less than or equal to the input's sum, right? So we are not creating new money, but we can spend less money than is getting in the transaction, right? And this money uh, is to be considered a I don't like the name fee. It's more like a tip because someone will do a service in the network, a security service in the network, and this specific guy will be able to redeem this difference here. This will be called mining in the thing in the system, right? So the mine
Oh, okay. So the tips are for the validators.
exactly.
I see.
And I will say exactly what mining means and exactly what the mining what the mining is doing to the network to validate this transaction because he's doing one very specific kind of validation here and a very special and very important one.
Okay, so the incentive to people to validate those hashes comes from the tips.
Comes from new coins that are issued in the as a result of this mining process. But people that are using the system can also tip the validators so they have more incentive.
Uh, I just want to add, and this is probably something you will mention later, but this emission of coins is also capped. At some point, the new coins will run out, and then there will only be the tips to pay for
Exactly.
that
This
service.
will happen somewhere around 2140, the year 2140. And
Okay,
I will present more details about this when we are talking about mining in
okay,
a
but
later.
yeah, but then the question is, so until then, aside from the new tokens being new coins being created, sorry,
Yes.
every the tips are just at the mercy of the users.
Yes, but you'll see there are economic incentives for people to do this because in practice what happens, there are more transactions being issued by second than transactions that can be fit in a block.
Whatever
So
that means.
yes, okay, but let's put this way, the flow of create of transaction creation is higher than the flow
Of
of
transaction
transaction.
validation.
Exactly. I would say transaction settling in the blockchain.
Okay.
So we need some I would say rule, but some kind of way to decide. Okay, which transactions I will validate and put in the blockchain, right? So there is an economic mechanism going on here because people can pay for the transactions to be more important or to be included
Ah.
in the block
Oh,
before.
so the
You
tips can
just,
also be
you
used as
just
a
need,
system of priority.
yes, in practice it will have it's used as to decide the priority of transactions.
Okay.
but you have to understand you are paying for this service, and if you pay more, I will serve you faster. It's like this.
Okay.
This is pretty much the rationale.
Okay.
All right.
Yeah.
Okay. So this is the transaction. Uh, and I would like to ask you guys if you want to stop here now or if you want to go into script. I believe I need 10 minutes to cover this part.
I think we have 10 minutes. I think it's all right.
Okay, so let's talk about Bitcoin script and how this cryptographic puzzles work. And the script is actually making money programmable in the system, and I believe this will be the part you will like the most. So let's understand this specific example, right? So if you go into the blockchain and look at the two transactions that are involved here, the first one is the one from the ninja guy. The ninja guy created coins, and he put this puzzle here, which is written in a specific programming language that's called script in the Bitcoin system. And Alice takes this and provides some data that can also be a programmable data here, like with if, else, and stuff like that. And together, those two things uh, will be considered a computer program that has to be run by the validators, right? So each part here, I'd like to understand this as the ninja guy here creates a locking script, something that locks value into the system, and Alice actually provides an unlocking script, something that will unlock value in the script, right? So the programming language semantics here is that of a stack based machine. So there's a stack, and you know how stack things work. So let's execute this program and see what's happening here. So we are executing the unlocking script first by convention. If it doesn't fail, we proceed with the locking script execution. Okay, and the whole thing we are trying to see what the whole thing do. So let's start with the unlocking script. So we are pushing some data into the stack. Here I translated the arbitrary garbage data into what they mean into the system so we can see better what's happening. So we are pushing some data into the stack, which is supposed to be Alice's digital signature. We are going to see why. Next, we are pushing more data from Alice that Alice is providing, which is supposed to be a public key. We are going to see why next too. Uh, we finished evaluating the unlocking script from Alice, and we did not fail, right? Failing is a condition that is pretty much uh, uh, it happens pretty much on purpose because there are some specific uh, instructions in the programming language that can fail. So, but pushing never fails. So we pushed stuff in the stack. So we just continue. Opdupe is for duplication. So we duplicate the top of the stack. And hash 106 consumes the top of the stack, calculates the hash of the data that was there, and put it in the top of the stack. So now we have uh, the Alice's public key hash. And one thing that I would like you to notice here is that this hash or uh, an address or this is how it's called in Bitcoin. The hashes of public keys are called addresses in Bitcoin space. So this address here was computed from information Alice has to provide in the transaction, right? So she has to know this public key here to produce this address that is here on the stack right now. Next, we push more bytes, and those bytes here are also an address, but this address here comes from the ninja guy. The ninja guy said, I will write this address here, and this is the data, right? And the next instruction, and now is how things are getting more interesting. Equal verify will consume two slots of the stack, and it will fail if they are not equal, right? If they are equal, it just continues without producing any new data into the stack, right? So what happened here? I will go back a little bit. Alice provided a public key. The validator computed an address based on something that Alice knows, and the script compared these to an information that was given by the ninja guy, right? And if those equal, this proves that Alice indeed knows this public key that creates this specific address, right? And this is done, it's a little bit convoluted right now, because if this is a public key from cryptography stuff, why not Alice just give it to the ninja and the ninja guy put into the transaction, right? So there are some privacy issues involved in this decision, because like it is in this example here, we don't have to reveal our public keys. Only we only reveal public keys here when we are trying to spend some money. But once we spend money, it's gone. Nobody can do anything to stop that, right? But if someone knows my public keys and knows that uh, and a specific public key is mine, someone can see the transaction, the previous transaction, and say, "Oh, Edu is getting some money. Let's get him and put him to jail or something." Right? So there are some privacy issues related to this. This is not perfect, but this is an upgrade on privacy.
I have a question.
Yeah. Yes.
Does Alice or anybody else has access to the Ninja Guy's script?
Everyone has access to the Ninja Guy script because it will be this part here will be part of the previous transaction that will be written in the blockchain, and everyone has access to the blockchain.
Okay, so my question now is, the
Yes.
OP hash 160
Sure.
applied an operation on top of what Alice has provided before.
Yes.
So it, because we first duplicated the public key, then we
Yeah.
applied the hash. So again, whatever it is in that box, or whatever is on the top of the stack, we're going to duplicate and we're going to hash it.
Mhm.
Then there is an operation called push bytes 20 that
Yes.
uses what is on the top of the stack as well again.
No, it's pushing new data into the stack. It's not using anything from the stack. It's not consuming anything.
But it's saying there that it is push bytes 20 and an Alice's public key hash.
Yes, it's
That's
the data.
that's the argument to the instruction. It's not on the stack yet.
Exactly. Look at this stack here. With this is the stack. We are going to duplicate what's in the top, right?
Yes. Yes.
Okay. Now we are hashing what's on the top.
Yes.
And now
Okay.
we are pushing more data. So there's a new data there.
Yeah, we are pushing more data, but my understanding is that the push bytes 20, there is an angle brackets. Alice's
Mhm.
public key hash is not that push bytes 20 is not utilizing Alice's public key hash.
No, this is something that the ninja guy has to know. This is the ninja guy is saying. This is the way the ninja guy is saying. This is the person that I will send this coin.
Oh, okay. So the ninja guy needs to know beforehand what is going to be the
Yeah,
result of the Alice's public key after being hashed.
exactly.
So
And
that's how we
how
know if
does
Alice is
how does
Alice. Okay.
exactly how does he know that Alice takes her public key, hashes it, and This will be called an address, and her she gives this to the ninja guy.
Okay, now
The
it makes
address.
sense.
It doesn't make sense.
Yeah.
And we are checking with the script if Alice indeed knows the public key that generates that address.
Yeah. Okay, that's fine.
Fine, right.
Yeah.
So next, the last instruction here is checking a signature, a digital signature. So to check a digital signature, we need three things actually. That's digital signature itself, which is there in the stack, the public key associated with the private key that created the digital signature, which is in the stack right now, or at least we believe so. And it needs the message that was signed. This is not in the stack, but this is public information. This is the transaction that already is in the blockchain, right? So we have all information to check a digital signature here.
Okay, so this
So
operation does a lookup in the blockchain?
not necessarily because it only needs the TX ID of the transaction that is being signed. And the software actually he can you can when you will start a node, a Bitcoin node, you will the first thing the node will have to do is to download the blockchain and scan the whole thing, verifying the whole thing, right? And it will have to validate the whole thing. And in this process, it will notice uh, if there are transactions that are related to addresses that my node controls. So I take notice of those things, and I cache those things. This is what is done in practice. So I don't have to go back into the blockchain and scan the whole thing
Okay,
again because
I'm gonna
cache the
change my question.
whatever.
So,
Yeah.
do I need
So
to do a lookup at somewhere outside of the
yeah,
stack?
outside of the stack. This is a very good question. I have to check.
Because it feels to me that they had an idea of like, let's make a stack-based programming language, and then the idea fell apart when they like.
Because yeah, I understand your question now. I will have to check the source code, what's happening in detail, right?
Mario must be pissed right now.
Yeah, because
Not
if he
really.
has
This is
if he has to check something that is not on the stack, this will be some kind of oracle in the system, right? In the
That's gonna
programming
be a
language.
side effect. That's gonna be a non-pure
Yeah,
function.
side effect. Yes, right. Yeah, I'll have to check. I have no answer for this.
Marinho?
Very good
it
answer.
certainly looks like a side effect. I would guess it's probably some kind of dynamic binding because I imagine that the number that the check signature needs to refer to, which is the transaction that has been signed, is probably set up when the environment that the script will
Oh,
execute
like a
in
global
is being
variable.
prepared.
Yeah, but this is a problem because the rationale of this thing is to validate a transaction, I should be able to do it using only the transaction data.
No, but maybe you do have in an environment
But
the
the
transaction data.
transaction it's no no but
Yes,
like the
but
transaction itself it
I know
contains the
the
script.
transaction itself. It's
Yeah,
part
yeah.
of the transaction data, right?
Yeah, the script is part of the transaction data, but also maybe this number that it needs to check against is somewhere else in the transaction.
Yeah, I have to check it. I will check it. I will check. This is a good question.
Yeah, but like, does it? Okay, but even if that's the case, Marinho, do you agree that this really seems like a side effect?
It is a side effect.
It
Okay,
is a
so
side.
the idea of using a stack fell a little bit apart. Eh.
Eh, kinda. I mean, Fork traditionally is a very low level language and it has side effects the same as you would find in C, for instance. So
Yeah. This is
Uh,
like assembly language for the system.
no, yeah, that's fine. That's completely fine. We are making one. I think that's fair. But we don't have this notion of being able to magically grab a value out of somewhere outside of the stack.
But I will check what's happening here. But I believe you need some kind of side information, yes,
Okay, continue.
to verify signature, based on what's here. This is a very good question. This is why I like you guys. So let's consider that this is a valid signature for the whole thing, right? So it will produce this is specific instruction will produce the value one, which is interpreted as true in the system, if the signature is valid. And the signature being valid proves that Alice knows the private key that creates the public key that creates the address that the ninja guy inserted in the locking script that he created before. Again, with this, Alice proved that she knows the private key that generates the public key that generates the address, which is the public key hash that the ninja guy established as the owner of this coin.
Not quite. She proved that she knows a signature, which she provided. She
But she
proved
can
that
only
she knows which
yes,
public key is a sub.
she can only build a signature if she knows the private
Yeah,
key.
maybe she got
No, no, no,
stolen.
no, 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 no. Here's what I'm getting at. Maybe somebody else produced the
Yeah.
signature and handed the signature plus the public key to Alice, but Alice doesn't know the private key. And then Alice sends the
Yeah.
message on behalf of this other person.
Yeah.
Sure,
That's perfectly possible here.
okay.
Yeah, that's definitely possible. Or she got stolen, which is like,
But
She
you
wouldn't
agree
be
that
because
whoever that if we did this, someone else is authorizing Alice to unlock this transaction.
yes,
In practice, it doesn't.
that's
We don't need to say Alice is the owner of the thing. Whoever is the owner authorized this transaction here.
yeah, no, that's fine. But I'm saying that if somebody else got into Alice's computer and private keys or whatever, they
Oh
could.
yeah. If someone gets your private key, it's done.
Yeah, yeah. But
It's
then that's the
it's
problem because they can falsify being you because they now have access to all the information required for the locking scripts.
yeah, but you see, from the perspective of the system, there is no fake in here.
There,
The
no,
fake,
that's true.
the faithful owner of the coin is whoever knows the private key and can produce the right signatures.
Yeah, that's true.
So the this is why people and this is a problem in practice because now you have to keep a secret with yourself to own a Bitcoin. Part of owning a Bitcoin is to be able to know this secret and to keep it secret and not lose it and not forget it somehow. So
Yeah,
you have this uh, it's a custody problem.
yeah, yeah.
You see,
That's for sure.
which is something that banks actually solve because with gold we also have a custody problem because if I have gold in my place here, a lot of gold, I would probably need a vault in my place, in my house, and I probably would. It also would be a good idea to have a militia to protect this thing. You can understand. We also have custody problems with gold and silver and whatever. Banks do this on our behalf, but here is something quite more complicated, I would say, because if I give my private key to the bank is the faithful owner of my bitcoins.
Yeah, pretty much.
I cannot spend my bitcoins anymore.
Yeah.
You agree with
Yeah, yeah,
this,
yeah, yeah,
right?
but that's partly solved because two things. You are supposed to be the owner of your keys, and second, the keys are not IDs that somebody can knock on your house and say and know that you are the owner. They don't know your
Yeah.
address because it's not an ID.
No, it's not an ID. It's a key.
Exactly. So that's partially solved. The custody
Well,
problem is partly solved because the anonymity involved.
yeah.
which also has bad things related to that. But the plus side is that the custody problem is now much easier to solve. Because if you have a militia protecting your gold, everybody can see the militia.
Yeah, but here I can write my private key in a piece of paper and hide this piece of paper. It's not that hard to do it
And that's
actually.
also so hard to lose the piece of paper. So,
Of
well,
course, but I can make some copies of the piece of paper and go into banks and put those piece of papers in real vaults in real banks with real militia protecting this, right?
go on.
You can understand this, right? It's easier to protect data than it is to protect physical things,
Yeah, that's fair.
right?
Yeah, you
All
gotta be a
right.
little bit careful because hard drives are a little bit flaky, but aside from that, it's fine.
Yeah, sure. That's why people say backup and whatever and all that kind of stuff, right?
Paper
So
wallets.
I'm going to stop here because my next stop is public key cryptography. So I will save it for a next session, and I will add more details than I have right now because I intended to just go through this, but since we are stopping here, I will actually add the math behind the thing so that you understand why these things work. And it's very interesting in general to understand the thing because it's useful for other systems, not only Bitcoin.
Okay.
This is the general cryptography.
Okay. So I
Right?
guess we have space for questions now. So do you have any
Sure.
questions? I don't know if I have a question. Let me think. Um, okay, maybe that's a tricky one, right?
Mm,
That's a tricky one. I don't know if there is a very easy answer.
yeah.
Why, aside from maybe being a fourth lover, why they decided to use a stack-based programming language?
Ask Satoshi. I have no idea. Asking Satoshi is not the right answer. Actually, we can discover this. Because in the original Satoshi client, as it was called in the beginning, the client that Satoshi originally open
Developed?
source, yes, there was no programming language embedded in the system. There was only, you see, the fields are called script pub key, which is supposed to have a pub key data, and the other field is called the script sig, which is supposed to carry data, signature, digital signature,
Yeah.
and that's it. And the system would be the validation would be like a fixed pattern checking, right?
Sure.
Someone I don't remember who was on the mailing list suggested this adding this embedded language which was accepted and developed right in the beginning of the system. But we probably have a record of the conversation, of at least of the public conversation that happened to justify adding the embedded language.
No, no, no. I'm sure you guys needed an embedded language, but my question is why it necessarily stack-based?
Yeah, I don't
And
know. I don't know.
yeah, but
I
Which
given
have a
I
the
can try to
responsibilities of
translate.
it, my feeling is
Yeah.
that it was probably the easiest way of making, because I don't know if
Yeah.
you're aware of this, but stack-based programming languages are probably the easiest way to have a Turing complete system in computer science.
This is an interesting thing. This programming language here is made uh, non-Turing complete on this by design.
Yeah, that makes
So
sense because if you have a Turing complete language, you can cheat. Uh,
maybe you can cheat, but the concern here is that if I have, for example, a Turing complete thing, I can write this. I'm trying to attack the system. I can make a transaction that loops forever, and the validator will be looping forever, trying to validate the thing that will never validate,
yeah,
that
yeah,
will
yeah,
never.
that's true.
So this is a kind of denial of service attack.
Yeah, that's
So
fine.
they are trying to avoid this.
Yeah, but Marin, do you have any thoughts on why they chose stack-based?
Simplicity of implementation,
Yeah, that's my
essentially.
feeling as well.
But
It's the
also,
easiest way.
there's a second point here. Notice that this validation works by concatenating two programs.
Mm-hmm.
Yeah.
That's easier to do in a concatenative language to begin with.
That's fair. That's fair. I would say that you can concatenate programs in if it's simple enough. You like I don't know in C, you can concatenate stuff with macros and
But
whatever.
but if you concatenate programs that are written in, I don't know, C or some other register-based language, now you have to agree on which registers will receive which arguments, which is less of a problem
Oh,
in a
that's
stack-based
true.
language.
That's true. Okay, that's true. That I'm convinced. I'm more convinced by that argument. So that your proposal is that because the common data structure of use is a stack in both cases, it's already agreed by convention what's going to be the thing when the programs get concatenated.
Yeah. Uh,
That's fair.
this is the problem of naming, scoping, hygiene, all over again.
Yeah.
Stack-based, you avoid that problem entirely. You just sidestep it.
Yeah. Okay, I'm satisfied with that answer. Even though we're gonna have to, I don't know, we don't, I don't know if I know the answer. Even if we check the public records,
Mm-hmm.
I am convinced that because of the simplicity, because this is the easiest way to make whatever language Turing complete or not,
Mm-hmm.
and because of the what Marinho said about when you concatenate programs, if it was a register-based programming language such as C, people would have to agree upon certain registers. So where is the data coming from the other script? I have no idea. But if you have a stack-based programming language, this convention is already asserted because it's always the stack, because it's all that you have.
Yeah.
Well, that's not entirely true because you can have
You
stack
still have
programming
to.
languages that have like special registers, but eh, that's fair.
Yeah. Regarding this specific part of the system, embedding programming a programming language here, uh, there are things that are quite interesting. For example, Ethereum is one difference of between Ethereum and Bitcoin is Ethereum is doing Turing complete computations on the transactions by design. So they have more powerful smart
But do they
contracts.
suffer from what you said, infinite loops?
I would guess not, because to run a script on Ethereum, you have to burn gas. I imagine that that's
They
done
have
per
other mechanisms
computation step. So
to
if you
avoid
just
this.
loop forever, eventually you'll just run out and stop.
Yeah. And the gas is kind of a concept of uh, making the running something on the system expensive for someone who's trying to run something on the system.
Oh, so they
Because
punish you
here,
if it's not performant.
yes, because here it's free.
Ah.
I'm a participant of the system here in Bitcoin. I can send transactions to everyone, and I'm not paying them to run the transactions, and they have to validate the thing.
Ah, I see. So
Here it's
they punish.
free.
Okay.
In Ethereum, they have this concept of gas. That's a token in the system that you have to pay for running scripts.
Mm,
So
okay.
they're right. So this is a their security mechanism for this. Another interesting thing that you can imagine here is nobody actually knows if the current Bitcoin script is indeed non-Turing complete. There are some controversies here, right? And there is why where does controversy comes from? There are some guys recently that are trying to build a, let's say, high level language over this, as you can imagine, and it's called Miniscript, and it may these guys maybe maybe not have found a way to do looping in using this language. So This is more or less
Okay, does the
controversial.
does the base language have conditionals?
It has if else conditions, but it doesn't have loops or jumps
Yeah, no, I don't understand. But if the
or or,
let's
or
if
ways of or ways of messing with the stack, if not by consuming or pushing from the top of
I
the stack.
have an idea of how that may be accomplished, even if the Bitcoin script is not Turing complete.
Mm.
If the loop, if the number of iterations in the loop is known at compile time, you can just compile the loop away entirely.
yeah, but that's cheating.
Yeah.
No, it's not.
It is, man. Because if you know ahead that how many iterations the loop is gonna go, you can basically like do line by line instead of having a loop.
Inline it, right? You can unroll the loop, right?
Yeah, but that's the case. Is the number of iterations known at compile time? Do you know that? Do you have a feeling of that?
Depends on what you're trying to do.
In the most common use case of this, which is to verify the
This
authenticity.
one, this example that I showed you is like 85 to 90% of transactions currently being done in the system.
Okay, so now let me ask you a different question.
Not
The
this exact,
remaining 20 to
just a second.
15%, will that
Just
use compile time known iterations?
there are no iterations here.
No, but I don't know about the 20 remaining percent.
I have no idea. You have to go into the blockchain and see what's people trying to do,
I see.
right?
Okay.
All right. I put in the chat
I'm
a
gonna
link
put
to
those links. I'm gonna put those links in the description. That's fine.
there are links to the script opcodes, and you can read more about this. I put links to the mempool space explorer of the transaction that we are analyzing in this presentation. Link to the white paper and link to the Bitcoin source code.
That's awesome. Okay, so if you
Yeah.
don't have any questions, I'm gonna end the recording. Does anybody have any questions? Nathan and Mars, you can write that in the chat if you want, if you have questions. This photo. Oh, bro. Okay, so Marinho, do you have any questions?
Question.
I'm fine.
Okay,
All
Nathan,
right.
I don't know
So,
if I don't think Nathan has questions. So yeah, so I'm gonna finish the recording.